Hello, my name is Vladimír Chmelko. I am from Slovak University of Technology in Bratislava, and this is our contribution to this conference. Title is Specifics of Fatigue Strength Estimation for Bicycle Frames. At the beginning, I defined our approach for the fatigue life assessment of bicycle frames are based on the two input parameters of the two sets of input parameters. First set is parameters of loading, then second set, input set, are parameters of materials, cyclic parameters of materials. Joining these two inputs, this is the hypothesis of fatigue lifetime accumulation, appropriate hypothesis, and as outputs is the distribution of fatigue lifetime in the statistical or probabilistic form. This first slide is about the materials which are used in the nowadays the producing of bicycle frames. Steels, these are relatively older materials, but are used in also today's for high performant frames. Then aluminum alloys, this is most usable materials today, and the composite materials based on the fibers from carbon or fibers from glass. For the assessment of fatigue lifetime, it's necessary to determine the appropriate loading process. Here are documented the process how we try to determine this important loading state. For the bicycle e-bike was determined 4 important loading state as a upward stairs downward, then jump and overcome the ditch. And during this operation was measured this operational state by the accelerometers, which are situated inside the tube of this e-bicycle frame, and also was measured by the strain gauges, which are situated on the tube between the rear and side tube. Here's the short video from this measurement of loading process, loading parameters, dynamic parameters of operation in front of our faculty. Based on this measured data, after some processing of this data as a filtering and other things, has been possible to define the dynamic factors in these key operational states in the ditch, stairs, and jump. Down on this table are documented these results as a dynamic coefficient in the vertical, lateral, and longitudinal direction. Due this 3 operational state, all this measurement was made under 24 psi as a tire pressure, which is recommended by the producer. It's possible also compare this measured data from the standards, which also prescribed how was necessary to load this frame in some stand in laboratories. This is not so important for this presentation, but it's possible to compare. Important is define these specifics for fatigue life assessment when it's clear what is the operation. I mentioned all 4 and then deeply described all of this. Then first specific is multiple technologies which are present in the frame production, and these multiple technologies lead to the different material properties. Second specific is the fatigue life assessment of welds. Welds are very complicated things for fatigue life assessment, and the specifics are also present in this frame from aluminum alloys or from steels. Then is the effect of geometric inaccuracy of fatigue life. And last, it's possible to determine as a multi-axial stress state, which is possible to consider in the assessment procedure. Technological processes. From this table is possible to see the different tensile properties caused by different technological process in the producing of these bicycle frames. For example, liquid die casting is one process, forging is different technological process, low pressure casting, die casting or hydroforming, these are typical processes for producing procedure from the aluminum alloys, and all these procedures lead to the different tensile properties as a yield stress and tensile stress, ultimate stress, and it's clear that this procedure also leads to the different and rather different fatigue properties of this material due to these technological processes. Here is documented the diagram in the form of SN curve. Top SN curve is the aluminum alloy 6061 in the temperature state T6. This is the top SN curve. In the middle is the same material without this T6 temperature state. And as a comparison, down in this blue line, this is the SN curve for additive manufacturing process. That it's possible to see this rather different cyclic properties. For the bicycle frame, it's necessary to define the appropriate diagram, which considers also the effect of mean value, because loading processes on the bicycle are based on the process with R equals 0, that relatively from 0 to the maximum peak, that this is the influence of mean stress and also effect of amplitude. Here's the problem with weld joints. Is the second problem in these technologies. Weld joint is a very complicated part for fatigue life assessment. Exist few approaches how it's possible to do. Also was included in standards. Another problem is that this weld process on the bicycle frames is more complicated due to the non-constant thickness of the wall in these tubes. These e-bikes have modification of thickness of this tube around the circle, around the surface, and on this picture is very good visible that in some parts is well welded material, and some part is very non-sufficient welded material, and then this is the additional problems for assessment of fatigue lifetime, because it's very complicated to determine the appropriate fatigue properties of material of this joint. We try to assess or test this weld joint. This is the weld joint directly from producers. This is reality, and this weld is for us relatively very simple, because this weld for this testing obtain SN curve was relatively simple. This is the circle with constant thickness of this tube. Now, how it is possible? How is visible? This weld process is very not appropriate, or have no appropriate parameters. This adjustment of these parameters was not appropriate, and lead to the very bad weld with insufficient welding of thickness. And in the comparison of this diagram, it's possible to see that basic material in the form T6, this is the aluminum alloy 6061, this is the SN curve on the top. This middle is SN curve for weld joints, when this weld joint is appropriate and right to do. And down this black points, this is the real results from testing of these two tubes, recalculated as a nominal stress, and these points are rather lower and have or lead to the very low allowed maximum amplitude stress for this insufficient weld. This is very surprising fact, but this is the reality from the producers. Here is another technological process. This is the die casting. Also, this process can lead to the problem as a porosity, as a bubbles. These bubbles decrease the cross section, and also these are the point in which can start the fatigue crack, as is documented also on this picture. Another problem, another specific on these bicycle frames, which influence on the fatigue lifetime, is the geometric inaccuracy, which is for the first view not so visible by eyes, but it's possible when you measure it relatively precisely. It's possible to see on these pictures that, for example, non-parallelism between the heat tube axis and saddle tube axis, as is documented on the right picture on the top, can lead to the additional stresses in the frame, which are non-considered when geometry is perfect. And when it's non-perfect, on the simulation, it's possible to obtain the results documented in this table down. When deviation is zero, that geometry is perfect. Maximum stress in the most loaded points on this frame is 67 megapascal. When this non-parallelism is 1 degree between these two axes, this maximum stress in the same cross-section increased 2 times, 154 megapascal. But these are the additional loading which is not considered in the standards assessment. But reality is that this inaccuracy is real, is present in the real frame, and is necessary to consider the specifics to the fatigue lifetime assessment. This perfect imperfection in geometry is possible to evaluate or obtain only by direct measurement. It's very complicated to create a right simulation without the measurement that we measured. These additional stresses here situated on this tube, the rosette strain gauge rosette was situated during this operational measurement documented on the previous slide of this video, and the shear stresses which are present due to the geometrical inaccuracy between this front tube and saddle tube are this red diagram. These are the shear stresses during the riding, and this blue, these are the weightable stresses. These are stresses from bending, which are possible to measure by this strain gauge. These are the stresses in this point, but this tube, this part, is part which join the seat tube and heat tube, and loading here is relatively stable without the big gradient. That is relatively very valuable results of the shear stresses. In standards are not present these shear stresses because standards not considered the geometrical inaccuracies. Reality is with these red stresses and are comparable with these weightable stresses from bending when we see these values. When we confront these stresses from the simulation with ideal geometry, with stresses from measurement on the real geometry, here's the measurement using the DIC, the digital image correlation, and here are the results from the finable method. This is the ideal geometry, here's the real geometry. Also, these differences is possible to see. Are not so is not possible to absolutely omit it, and this difference between real stresses and ideal simulated stresses is also necessary to add in the assessment of fatigue lifetime, and this is also one of the specific of the not only the bicycle frames. These additional stresses from the geometrical inaccuracy in the form of shear stresses, for example, from the additional torsion, lead to the multiaxial stress state. And multiaxial stress state is region very complicated, very long time discussing on the conferences. Here is only documentation when we apply 4 different approaches for multi-axial fatigue, from the Findlay approach, Dangwang approach, DMC, this is our from our university, and from using the von Mises formula, it's not visible on the right. These different approaches lead to the different damage is visible here, and different fatigue lifetime in the hours based on the loading process which we measured. And these differences are in 2 orders, yes, 5 hours and 180 hours. At the end, it's possible to conclude this sum of specific of assessment of fatigue lifetime in bicycle frames. This first is multiple manufacturing technologies which are in present in the frame production, and these different manufacturing technologies lead to the different cyclic material properties. This is the fact, and it's necessary to consider it. Second problem, and second specific, are the welds. Not only welds in general, specific kind of welds which are present on the bicycle frames due to the change of thickness around the cross section. These parameters of welding is very complicated to adjust appropriate, and then lead these welds for lower SN curve as we wait in the weld joining. Second specific is the effect of geometric inaccuracy on the fatigue life, which create or induce additional stresses, additional loading. In majority cases, this is the additional torsion. This additional torsion create additional shear stresses, which are necessary to consider also in this process of assessment of fatigue lifetime. This stress is possible to measure directly in the operation or directly on the bicycle frame on the stand. And this additional torsion, additional shear stresses lead to another specific, this is the last, this multi-axial stress state, which have many problems, is not standardized to this time, and selected of appropriate hypothesis of multi-axial fatigue for multi-axial fatigue, and considered right the cycles in counting method. This is all another specific which are present on the bicycle frames. Thank you for your kind